radicals. All right, so if we have the nth root of A and the nth root of B, meaning it's the same index, it could be 5 and 5, it could be 1,000,000 and 1,000,000, as long as they're the same index, then I can rewrite it with a radical on top divided by a radical on bottom, or the index of the quotient of that fraction. All right, what you want to think about is these go both ways. If you're given one fraction, if you're given something like this on the right, you can write it this way. If you're given it this way, you can write it this way. Okay, this goes both directions based on however the problem is initially set up for you. All right, an example would be if you were given square root of 18 divided by square root of 2. This property lets us write it as a square root with one big square root symbol of the entire fraction. Simplifying what's under that radical before we even do any square rooting. We're just going to simplify what's under the radical, and we end up with square root of 9. Square root of 9 we can do, which is 3. All right, but the biggest thing from this is that this goes both directions. If you're given it in this step, you can rewrite it as this step. If you're given it in this step, you can rewrite it. Okay, being able to go back and forth. Okay, let's do a couple examples with this. So we know this one would be big square root symbol, 243 divided by 27. Cole's punching that away. Cole, what is 243 divided by 27? 9. Okay. And again, I'm not testing you if you know that mental math, if you can do 243 divided by 27. Put it in your calculator. Okay. What is 243 divided by 27? Oh, that's 9. I can do square root of 9. That's easy. That's 3. All right. So what may look intimidating, or some of these problems can look intimidating because there's lots of stuff going on. Square root of 243 over square root of 27, I don't know what that is. Start breaking it down, okay? Oh, now I can get to a point where I can solve this. Isn't so bad. All right, this one, we're going to write it as one big square root symbol with the fraction underneath. So now let's just simplify that fraction. 12x squared divided by 3x. So first I would look at the numbers. 12 divided by 3, well, that's easy enough. That's just 4. X to the 4th divided by x. And again, x to the 4th just means x times x times x times x. 4 x's are on top. And on the bottom, I only have 1x. So I could take 1 from the top, 1 from the bottom. That's a useful form of 1. All I'm left with is x cubed. Or we know when we have exponents in a fraction that we just subtract the exponents. So 4 subtract 1 gives me 3 as well. Now again, this is a square root. So let's see if I can rewrite any of this as a square. Well, 4 I could write as 2 squared. X squared x. So if I take the square root of 2 squared, all I'm left with is 2 without a radical symbol. Square root of x squared is just x, but then I still have that lone x under the radical. So this would be 2x, root x would be final simplified form. And we are going to work all the way to final simplified form. All right? Anytime you have a number in your radicand position, some coefficients, always look at that index and say, okay, can I simplify that further? Squares, is there a perfect square factor of it? Cube, is there a perfect cube factor of it? All right, this one is one big cube root of 162 y to the fifth all over 3y squared. 162 divided by 3 is 54. Y to the fifth divided by y squared is going to be y cubed. So I can see already I have a cube root of y cubed, so I know I'm going to be able to bring a y outside of the radical. Now 54. So again, we're going through our cubes. So 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Is 27 a factor of 54? Yeah. So I could say 27 and 2. 27 is really the same thing as 3 cubed. So I could bring out a 3 times square root of 2. Or I'm sorry, square root, cube root. There we go. 3y cube root of 2. All right, so that's dividing. Straightforward. Write it as one big fraction. Or again, you can break it from one big fraction, -2 like this. You can rewrite it as two separate ones. Depends on the path you have to take to solve the problem or simplify. Now, we can also multiply to eliminate radicals. If I had square root of x times square root of x, what is square root of x times square root of x? Just x, because this is really square root of x squared. And this is what we're doing. If we have our index is the same as our exponent, that simply becomes x. So that's why I say sometimes we can multiply, and that will eliminate the radical right there. What about cube root of x times the cube root of x? What's that? Cube root of x squared. My index and my exponent do not match up. This would be as far as I could go. I did not eliminate the radical. But what happens if I took cube root of x times cube root of x times a third cube root of x? Well, then I would have cube root of x cubed. Now I do have that matching going on, and that's just x. All right, if I had fourth root of x, I would say fourth root of x 4 times. If I had 10th root of x, I would say the 10th root of x 10 times. All right, so that index is important if you want to eliminate the radical. It's telling you how many times you have to multiply through. So that's going to help us now with rationalizing the denominator. All right, this is important. When you're asked to simplify, and I will always ask for simplest form. If you give me a fraction that is 6/8, I want you to simplify to 3/4. All right, working it into simplest form, and I never say reduce. Okay, it's same. 6/8 is the same as 3/4. It's just that 3/4 is in simplest form. When dealing with exponents, never want a negative exponent. So if you end up with some y to the -2nd, I want you to write that as 1 over y squared. So we can move those up and down to eliminate. So this is just proper mathematical notation. Simplest form for a fraction is in the simplest. How far can we work it to? Exponents never have a negative. Radicals never in the denominator of your final answer. So this is rationalizing the denominator. Okay? We never want to have that in there. So what we will do, if I wanted to eliminate square root of 2, what could I multiply to eliminate that radical? If I multiply this by square root of 2, I'm going to end up with just 2 in my denominator. Just like we did in that last slide, square root of x times square root of x is just x. Square root of 2 times square root of 2 is just 2. So we've eliminated the radical in the denominator. Well, with math, if I multiply the denominator by this new root 2, I have to multiply the numerator by root 2 as well. So now this becomes root 2 divided by 2. This is simplest form. All right, and this is now going to be expected of you. Do not give a final answer with a radical in the bottom. We can rationalize the denominator by multiplying by another radical, or you might multiply by a couple radicals to fully eliminate a radical on the denominator. In this multiplying by root 2 over 2, root 2 over 2 is 1. X over x is 1. Infinity over infinity is 1. If I have the same numerator and same denominator, it's 1. If I'm multiplying by 1, it's not changing the problem. This is algebra. It's just manipulating it to get it to a form that we want. Okay. What am I going to multiply by on this part number 2? Ben, what do you think? Not, it's just square root. There you go. Okay. And I'm taking that whole thing. So square root of 3x, because I know square root of 3x times the square root of 3x just leaves me with 3x. But on top, I also have to multiply by that square root of 3x. So this gets into yesterday with multiplying, has the same index of 2, so I can multiply what's under the radical, and so that becomes square root of 12x. Square root of 12x, I can simplify that to be 4 times 3 times x. The bottom is still just 3x. The reason I'm breaking it apart, because 4 is a perfect square, so I can bring a 2 out. Square root 3x, all divided by 3x. Do not fall into a trap of thinking this 3x and this 3x in the bottom will go to that useful form of 1. I'm going to say cancel out, but that's the only time you're going to hear me say cancel out. Don't say cancel. They don't cancel. Okay? But you cannot just move stuff from a radical to something that's out of a radical and combine those and work with those. Okay? Under the radical, that's a completely different number. So we're going to keep that radical there. So it's 2 root 3x all divided by 3x. Okay. What am I going to multiply here on example 3? How can I rationalize this denominator? Sarah McMartin, what do you think? Okay. Give me your best guess. Right or wrong, we're going to build off of that. Okay. So we're going to multiply by 3 root 3. Okay. If I take a cube root multiplied by a cube root, is that going to give me 3 as a final answer? It's going to be cube root of 3 squared. So my index and my exponent are not the same. So we actually have to do it another time. All right, this is what that last slide was getting into. So a cube root, I actually have to do it 3 times to fully eliminate the radical. And again, I'm going to do it on top of each one. So I'm multiplying by the cube root of 3 twice on top, plus that cube root of x. But the reason I'm doing that is now the denominator is just 3. So the cube root of 3 times cube root of 3 times cube root of 3 is cube root of 3 cubed. A lot of 3's going on. My index and my exponent match. Boom. All I'm left with is 3. But now on the top, I have cube root of x times 3 times 3. So this is 9x. And this is as far as I can go. 9 is not a perfect cube. It's not the product of a number and a perfect cube. So this is as far as I can go. But this idea of rationalize the denominator is important, okay? Never have a final answer with a radical in the denominator. And if you have cube roots, fourth roots, sixth roots, this means you have to multiply it that many times. The index will tell you how many times you're going to multiply on the bottom. All right, last thing we're going to talk about is a couple short examples, and you'll be off and rolling. So this idea of rationalize the denominator is important, but sometimes we can use the property that we started with and rewrite it as one big radical, simplify what's under the radical, and that takes care of rationalizing, okay? And we'll do a couple examples here to further explain what I'm talking about. All right, then if you still have a radical in the denominator, you can rationalize and simplify. But the first thing when you look at it, like, oh, shoot, I got some work to do here, look to see if you can write it as one big radical with a fraction, simplify that fraction, and that might take care of your radical right there. Okay, all right. So this one, I'm given two separate radicals, and I have a radical in the denominator, so that throws off a red flag right there. Nope, can't do it. So what I'm going to do, I'm going to write an equivalent big radical that's 21x to the 10th divided by 7x to the 5th. So again, that property allowed me to take two radicals in a fraction, rewrite it as one radical with the fraction in the radicand spot. And the benefit of doing this, 21 divided by 7, oh, that's nice. That's 3. X to the 10th divided by x to the 5th is going to be x to the 5th. Do not make the mistake here of doing 10 divided by 5. Remember, these subtract. So this is 3x to the 5th. I'm square rooting this, so let's keep going. So this would be 3. I can't write that as a perfect square, but I could write x squared, x. And so I have two x's that I'll pull out. So that's x squared times 3x. So this one, I started with a radical in the denominator. I didn't even have to rationalize this denominator. I still got to the correct answer. Okay, last one. Cube roots of 4x over x squared. So we know we could write it by doing cube root of 4x on top, cube root of x squared on the bottom. So that's what I mean. I have that radical on the bottom. So I've almost jumped a step. Well, this one can be simplified. This is really just cube root of 4 over x. All right, so I would have had, there's only one x here, there's 2 on the bottom. X over x would be that useful form of 1. I still would have an x on the bottom. Okay, so now I could write this as cube root of 4 all over cube root of x. Because it was a cube root, I'm going to need to do 3 total on the bottom. So I end up with just x. But then on the top, I'm going to do cube root of x and cube root of x again. So I have the cube root of 4x squared, and I'm done. Can't go any further than that. All right, so what I mean by do the work first, write it as one big radical, see if you can divide. This one we could divide. Simplifies the process, gets you to the end result a little bit easier. Got it? Here we go. Some problems for you to practice. Take a couple board problems out of there. Tomorrow we'll do one more lesson. Friday will be an easy day.